Hi, my dears. Good morning. I welcomes you for the today's session about Faraday's law of induction. What is that? Faraday's law of induction. In the previous session, we discussed about different types of magnets and their characteristics and their differences also we discussed in the previous session. Today, we are going to see one of the important character in electromagnetism, that is Faraday's law of induction. Let's see what is that. Faraday's law of electromagnetic induction. It is a basic law of electromagnetism. What is that? It is a basic law of electromagnetism. In electromagnetism, it is a basic law. Which one? The Faraday law of induction is a basic law of electromagnetism. Which, what is electromagnetism? It is an interaction between electric field and magnetic field. The interaction between electric field magnetic field can be considered as electromagnetism. So what is electromagnetic induction? What is the phenomena of electromagnetic induction? So here electromagnetic induction is nothing but when electric field or magnetic field, when if I going to consider magnetic field, when a magnetic field interact with the electric circuit. What is that? When a magnetic field is interacting with electric circuit, what is happening? It is producing electromotive force or voltage. Electromotive force, in other terms, it is called as voltage. When magnetic field is interacting with electric circuit, it produces electromotive force. It is also called as voltage. The production of electromotive force with the help of electric circuit and magnetic field is known as electromagnetic induction. Electromagnetic induction. To study electromagnetic induction, Faraday's laws are essential. So the Faraday laws is used to predict how a magnetic field would interact with an electric circuit to produce electromotive force. This is the main concept of Faraday law. It is used to predict how a magnetic field would interact with an electric circuit to produce an electromotive force or voltage. And this simple phenomena is known as electromagnetic induction. Let's see, before we are moving to the further concept, we would like to know some of the basic terms related to this electromagnetic induction and Faraday's laws. We begin with electromagnetism. Let's see what is electromagnetism. Electromagnetism is a branch of physics. It is a branch of physics which deals with the electromagnetic force that occurs between electrically charged particles. What is that? That occurs between electrically charged particles. It is a branch of physics. This phenomena is a branch of physics this phenomena deals with the electromagnetic force that occurs between electrically charged particles. So what are the electrically charged particles? You may consider the positive charge, you may consider the negative charge. So between this positive and negative charge, whatever forces existed, that is nothing but electromagnetic force. So here the dealing of electromagnetic force between electrically charged particles is known as electromagnetism. It also considered as a type of magnetism produced by an electric current. It is also considered as one type of magnet. We already discussed it in types of magnetic material, that is an electromagnet. The electromagnet, whatever phenomena, whatever properties it is exhibited, that is called as electromagnetism. So from that concept, it is also considered as a type of magnetism, a type of magnetism produced by an electric current, produced by an electric current. The electromagnetic force is one of the fundamental forces. Let's see what is electromagnetic force. So here we have four different types of forces in nature. In the four different types of nature, one of the force is electromagnetic force. That is the reason it is considered as the electromagnetic force is one of the fundamental force. One of the fundamental force. It exhibits what it is exhibiting. It exhibits magnetic field, electric field, and light. From this electromagnetic force, what phenomena we can analyze? We can observe certain phenomena, that is, from electromagnetic force, we can analyze magnetic field, we can observe the magnetic field, we can observe electric field, we can also observe light. So, in electromagnetic force, the electromagnetic force is one of the fundamental force, and it exhibits magnetic field, electric field, and light. These characters are exhibited by electromagnetic force. Coming to the what are the four types of the forces we discussed just now? There are four fundamental forces in nature. One is that electromagnetic force. Is it right? Let's see what are the remaining three forces in nature. So, as we discussed here, electromagnetism is one of the fundamental force, and the remaining three fundamental forces are weak interaction force. This is also called a nuclear. Weak interaction nuclear force. The third one is the second one is a weak interaction nuclear force. The third one is strong interaction nuclear force. The fourth one is gravitation. This is we know very well. So that is about the apple story of Newton. So here electromagnetism, weak interaction force, strong interaction force, gravitational force, these are the fundamental forces in nature. You can see the figure, the electromagnetism and weak interaction of the particles and strong interaction of the particles, and gravitation, which is nothing but falling off apple. So these are the four different types of force in nature. One is electromagnetism. This phenomena, so which one? The electromagnetic induction. The electromagnetic induction phenomena was discovered. So the induction phenomena was discovered in 1819. 1819. In 1819, a Danish scientist who discovered induction phenomena. The induction phenomena was discovered in 1819 by a Danish scientist. His name is what? A Danish scientist Ørsted noticed the needle on a magnetic compass mode. So here, how we notice that one? When a needle is changed, there is a change, there is a variation on the needle when on a needle. Notice a needle on a magnetic compass. So here the compass, in a compass the needle is moves, then there is a slight disturbance in the needle of magnetic compass. That from that concept we analyze this induction. So how why the needle is moved in magnetic compass? It was put close to electric coil. Here the compass, which one, the magnetic compass, whenever it is placed near the electric coil, whenever the compass is placed, which compass, the magnetic compass, whenever it is placed near the electric coil, inside a compass, what is the needle is, whatever needle is there, the needle is moved. So from this phenomena, a analyze this induction concept. So this is about the induction, but the laws are introduced by Michael Faraday, later him. So what are the uses of the electromagnetism? So here electromagnets produce much more powerful magnetic fields than permanent magnets. So what is the need of, what is the need of electromagnetism? From the electromagnetism, electromagnets are produced. What is that one? Electromagnets are produced. So these electromagnets much more powerful magnetic fields producing. That means electromagnets produce much more powerful magnetic fields than permanent magnets. So we have temporary, permanent, and electromagnets. These are the three types of magnets we analyzed in the previous video. So here electromagnets produce much more powerful magnetic fields than permanent magnets. The power of electromagnet. The power of electromagnets can be adjusted by changing the amount of current flowing through it. So here it is producing more powerful magnetic fields, and the power of magnetic field can be adjusted. You can reduce the magnetic field power, you can increase the magnetic field power by changing the current, amount of current. By changing amount of current, we can reduce or we can increasing the magnetic field power. The power of the electromagnets can be adjusted by changing the amount of current flowing through it. Electromagnets find their uses in many things that we use in our daily life. So in our daily life, whatever things we are using, in almost all, in almost every element, every component, every object, this electromagnet is a phenomena is there. Right now I'm using this mobile, I'm using this electronic device, and this electronic device is working by using of electro. There are other components also we have, but here electromagnets in my mobile to receive the signals, to get the data signal, or to connect with someone whenever I'm making a call. So I need some signals. I need electromagnetic waves. That means signal means what here? Electromagnetic spectrum. So the signals, everything will be for the calling, for the incoming, for the outgoing, to run the data. So everything is required because everything is possible because of this electromagnet. Inside my mobile's electromagnet is there. So you are watching on TV or YouTube or somewhere, that device also having electromagnets. So here electromagnets are useful in our daily life of elements, means things. So here they are used in cell phones. Just we discussed, they are used in cell phones that work on the interaction between the phone signal and magnetic pulses produced by an electromagnet inside the phone. So just now we discussed, for example, if you consider your mobile phone, how it will be interacted, how it is working. Your mobile phone is work on the interaction between the phone signal, between the phone signals and magnetic pulses produced by an electromagnet. See here, you can remember here, just here, work on the interaction between the phone signals and magnetic pulses produced by an electromagnet. Electromagnet work is what here? Interaction between phone signals and magnetic pulses. So here magnetic pulses produced by an electromagnet inside the phone. So this is the working concept of your mobile. Because of the electromagnet is interacting with phone signals and magnetic pulses, so that you are receiving calls, you are making calls, and you are getting data. So this is the concept. So coming to the electromagnets are also used in magnetic resonance imaging. This is nothing but MRI scan. You know very well about the MRI scan. What is the MRI scan? This is a special apparatus. So the whole body of the patient or person will be scanned by a particular device, that is nothing but MRI scan. So here the magnetic resonance imaging electromagnets are also used in MRI. So electromagnets are also used in magnetic resonance imaging. That helps us to look inside the human body. To thoroughly understand the human body, we are using MRI machine, that is magnetic resonance imaging machine, to understand the whole body of the human. So that is also works on the basis of electromagnets. Loudspeaker use electromagnets to produce sounds. So this is very well, we know very well about the DJ sounds. So here loudspeakers use electromagnet to produce sound. Electromagnets make it easy to handle large chunks of scrap metals via cranes. So to the electromagnet, so the what if an object fell down in water, to lift this object which are fell down in water, we are using cranes. So because of this crane, the crane having some magnetic property, one part of the crane is having magnetic property, and this magnetic property of body of a crane is attracting the scrap metals of the body which fell down in dust, which fell down in and different garbages which fell down in water, that everything will be attracted by these cranes, which is handled by electromagnets. Modern generators also require electromagnet to function efficiently. So the generators means the power supply devices. The generators are required electromagnet to work properly. So these are the some uses of electromagnetism. Let's see these figures, and see here there is a galvanometer is there, and there is a bar magnet in hand, right side hand, and left side there is a galvanometer. The galvanometer is connected to the electric circuit, and now this bar magnet is bringing towards the circuit of galvanometer in case 1. Then what we notice here, we notice that when we are bringing the bar magnet towards the galvanometer circuit, so the needle inside the galvanometer, so there is moving opposite to the this ball magnet. See here, we are pushing the ball magnet towards the galvanometer, but inside the galvanometer whatever needle is there, it is moving opposite to this pushing ball magnet. Check the second figure. So here the ball magnet, it is in stationary. So the needle of the galvanometer is also in stationary. So it is in stationary. So this is also it is in stationary form. Coming to the third one, see here the ball magnet moving away from the galvanometer, and you can see the needle in a galvanometer, it is moving away, so it is opposite direction. So both are in, so here bar magnet direction and needle of the direction, both are in opposite direction. This is a concept, or this concept is related to the Faraday. So before we are moving to this Faraday concept, we would like to understand what is exactly electromagnetism, how it can be useful. See here, there is, you have swiping machine. So here the person is swiping his card. Then recent time we are observe lot of cashless transactions. In this lot of cashless transaction, the transactions are happening without taking any card, without taking any uh, proof of element. We are simply doing the transaction. This is nothing but a cashless transaction. How the cashless transaction, how you are taking the money from the ATM, how you are scanning the QR code and ATM card transaction. This is how these all are possible. These all are possible. A mechanism that is also nothing but a physics mechanism is simply defined as electromagnetic induction. Electromagnetic induction is the process in which a conductor is kept in a particular position. So electromagnetic induction, there is electromagnetic induction is a process in which a conductor is kept in a particular position, that means constant, and magnetic field is varying. So this is there is a reason, uh, this is only which we are discussing here. This, if you are taking that one, this is the conductor and this is the magnetic field. Just imagine this is not conductor, but as of our understanding, this I am taking it as a conductor, this whole circuit, and this I'm taking that to magnetic field, because the field is created by magnetic field. A circuit is there, that is nothing but because of the conductivity nature, the current is passing. So this I can consider as a conductor, this I can consider as a magnetic field. So here what is happening, so here electromagnetic induction is a process in which a conductor is kept in a particular position and magnetic field keeps varying. This mechanism produces voltage or electromotive force across the electrical conductor. So here electromotive force or voltage is produced across this conductor. This is discovered by the Faraday in 1831. So that's the reason he introduced Faraday's laws. That is the reason he introduced Faraday's laws. What is electromagnetic induction? Because of the magnetic field, because of the electric circuit, electromotive force or voltage is produced. That phenomena is known as electromagnetic induction, and this is observed by this phenomena is observed by 18 by this Michael Faraday in the year 1831. Also he formulated some laws regarding this one, that is Michael Faraday's laws or Faraday's laws of induction. So this is another figure, so that is the same thing, this is in modification form. Just here we taking that one, the branch, this is nothing but metallic element, and metallic element is connected to the wires, and wires are connected to this ammeter. Then you will be see there is a reading deflections that will be indicating that one, how the magnetic field is interact with the electric circuit. That is also can be considered as electromagnetism phenomena. So there are, see, this is, we have the different types, there are different definition, but here these scientists are done many experiments there. As of their experiment, they given different definitions for the electromagnetic induction. So here the simple one, what is electromagnetic induction? The methods are different, but the final aim is that electromagnetic induction means it is an interaction of magnetic field with electric circuit to produce electromotive force or voltage. the importance of this law, which law? Michael Faraday or Faraday's law is what? The importance of this law is producing electrical energy in a circuit by using magnetic field. This is another modification form of the Faraday. So the machines like generator transformers will be working on electromagnetic induction, just we discussed right now. So here Faraday conducted many experiments to understand this great phenomena, and during these experiments he introduced some of the laws. The laws will be considered as the Faraday's laws of induction. So like that, in his all thoroughly experiments we got to important, he formulated two important laws, that is Faraday first law and Faraday second law. Let's see what is Faraday first law and second law. First, I am taking the first law. Any change in the magnetic field of a coil of wire will cause on an EMF to be induced in the coil. So here what is the thing? Any change in the magnetic field of a coil of a wire will cause an EMF, electromotive force, to be induced in the coil. This EMF induced is called induced EMF if the conductor circuit is closed. If the conductor circuit is closed, the current will also circulate through the circuit, and this current is also called as induced current. So here what is that one? Simple one. Any change in the magnetic field means magnetic field variation of a coil of wire will cause an EMF to be induced in the coil. Just like this is just another, it's just like an electromotive force, sorry, electromagnetic induction. That means if you have variation magnetic field, according to variation of magnetic field, there is a EMF is produced. So here, whatever EMF is produced in a coil, that EMF is considered as induced. Induced means what? Affected. Induced. So here, whatever EMF generated in a closed circuit, that EMF is called as induced EMF. So if you are taking a closed circuit, or if you are taking a closed loop, in a closed loop, according to induced EMF, the current also is generated. So whatever current is generated in a closed loop or circuit, that current is also called as induced current. So here somebody is asking how we can change the magnetic field. Method to change the magnetic field, but by moving a magnetic field, by moving a magnet towards or away from the coil. So here, by variation of the magnetic field, by moving or away from the coil. So what is happening? Magnetic field will be changing. By moving the coil into or out of the magnetic field. If you are taking magnetic field is constant, if you are changing the coil, so if you are moving the coil towards the magnetic field or away from the magnetic field, the magnetic field will be changing. By changing the area of the coil placed in the magnetic field. So here, if you are taking magnetic field, in the magnetic field, whatever coil you are taking, small size or big size or normal size, so the area of coil also will be changing the magnetic field. By rotating the coil related to the magnet. So here, rotating the coil related to the magnet. So here, these are some of the cases how to change the magnetic field. So coming to based on this above concept, and he formulated the second law. The second law states that the magnitude of EMF, which is generated in first law, the magnitude of EMF induced in the coil is equal to the rate of change of flux that linkages with the coil. What is that? It states that the magnitude of EMF induced in the coil is equal to the rate of change of flux that linkages with the coil. The flux linkages of the coil is the product of number of turns in the coil. The flux linkages of the coil is the product of the number of turns in the coil and which is associated with the coil. So here, let's see briefly. It states that the magnitude of EMF induced in the coil, whatever EMF is generated in the coil, is equal to the rate change of flux. What is that? Rate change of flux that linkages with the coil. In a coil, whatever flux is there, that flux will be changing, and that changing flux is equal to induced EMF. The flux linkages of the coil is the product of number of turns in the coil. Then how the flux is related to the coil? The flux linkage of the coil is the product of number of turns in the coil and associated with the coil. So here number of coils and associated with the coil. So these terms that we can consider, a simple one you can take as a capital N, which is indicating number of terms. So here let's see, we have another definition. The induced EMF in the circuit is equal to the, this is another simple definition. The induced EMF in the circuit is equal, you can use this one only. The induced EMF and the circuit is equal to the negative of the rate at which the magnetic flux through the circuit is changing with the time. So here this is a simple one and easy method one. The induced EMF in the circuit is equal to the negative of the rate at which the magnetic flux through the circuit is changing with the time. So here the flux with respect to the time changing and in the form of negative rate, that is equal to the induced EMF, and this is about the second law, and it is mathematically expressed as induced EMF is equal to epsilon is equal to minus n. You can use E or epsilon. Here I can term it as epsilon equal to minus n del phi by del theta. You can use d phi by d theta. That it is your choice. So here epsilon or induced EMF E equal to minus n d phi by dt. Simple one. The induced EMF in a coil is equal to the number of turns of coil and the change of flux with respect to the time. So that is the reason induced EMF E equal to minus n d phi by dt. Sorry, d phi by dt or del phi by del t. If somebody is asking why is negative, the negative is indicating opposing character that we can see in coming session. It is indicating the opposing character. Faraday's laws of induction derivation. So what is the derivation? Consider a magnet which is approaching towards a coil. Here we need to consider two instants. We need to consider what? Two instant condition. What I am taking that one? Just take a coil. So towards a coil, the magnet is moving. The magnet is approaching towards a coil. When magnet is approaching towards a coil, here for instant time t1 and for instant time t2, we need to take some flux concepts. So here whenever we are bringing this magnet, when magnet is bringing towards a coil, inside the coil flux will be generated. Is it right? Flux will be generated Now that flux we will be analyzed at time t1 and time 2. Now flux linkage with the coil at the time t1. What is that one? It will be considered, I take capital T1. So here it will be considered as what? It will be considered as T1 equal to N phi 1 Faber. N phi 1. What is WB? WB is nothing but units. That is nothing but Weber. So T1 equal what? N phi 1. Similarly, flux linkage with the coil at time T2. What is that? At time T2. Let's see what is time T2. That is T2 equal to N phi by 2. Sorry, N phi 2. Is it right? N phi 2. That is what? N phi 1. This is what? N phi 2. Coming to the another one. Change in flux linkage in a coil. What is the change of flux linkage at time T1 and T2? That will be considered as T2 minus T1. Is it what? T2 minus T1. What is T2 minus T1? T2 minus T1, that is N phi 2 minus N phi 1. N is a common. So what is that? N of phi 2 minus phi 1. If this change in flux linkage considered as, so here what is that? So T2 minus T1 equal to N phi 2 N phi 1. N is a common. Phi 2 minus phi 1. So what I am taking that one in the place of phi 2 minus phi 1, in the place of phi 2 minus phi 1, if we consider phi, what is that? Phi 2 minus phi 1 is equal to phi. Then what will be happen? So the change in flux linkage is considered what? That will be considered as N phi. Is it right? T2 minus T1 equal to what? T2 minus T1 equal to N of phi 2 minus phi 1, where phi 2 minus phi 1 is considered phi. Therefore it is N phi. Now the rate change of flux. What is that? The rate change of flux is what? The rate change of flux is considered as N phi by T. So the rate change of flux is what? The rate change of flux is N phi by T. The rate change of flux is N phi by T. Therefore, its derivative considered as considered as what? N d phi by dt. N phi by T. Its derivative is what? Derivative is d phi by dt. So derivative is N d phi by dt. Hence, the rate change of flux linkage. So what is that? T2 minus T. The flux T2 minus T1, that means the flux change, that is induced EMF flux change, can be considered as what? E equal to N d phi by dt. But according to the Faraday law of electromagnetic induction, the rate of change of flux linkage is equal to induced EMF. It is equal to induced EMF. Therefore, induced EMF E equal to minus N d phi by dt. According to Faraday law, it is considered as what? E equal to minus N d phi by dt, where phi is in Weber, phi equal to B a magnetic field and area, where B stands for magnetic field strength, A is the area of coil. Applications of the Faraday, that is the derivation. Coming to the applications of the Faraday law of induction, some applications of Faraday law of electromagnetic inductions are electrical generators which produce electricity, works on the principle of electromagnetic induction. Transformers, which use to change voltage of the alternate current, works on the principle of electromagnetic induction. Working electrical bells are based on electromagnetic induction. Faraday's laws of induction in daily life, that is above the induction cooker, works on the basis of mutual induction, which is the principle of Faraday's law. Electrical equipment like transformers work on the basis of Faraday's law. These are the daily applications of daily apparatus using applications of Faraday. Coming to the Lenz law. Lenz law states that the current induced in a circuit due to change in magnetic field is directed to oppose the change in magnetic flux and to exert a mechanical force which opposes the motion. So this is the reason we got minus in the formula. Lenz law states that the current induced in a circuit due to a change in magnetic field is directed to oppose the change in magnetic flux and to exert a mechanical force which opposes the motion. So that's the reason. This is a schematic diagram. This is the coil, and towards the coil, if you are bringing if the magnet is approaching towards this coil, so in coil the current is generated. Whatever current is generated, it is opposing the direction of the magnet. That's the reason we got minus. So that is induced EMF equal to minus n d phi by d theta. That is what induced EMF equal to d phi by, here I consider dou, you can consider dou or d phi. So here induced EMF equal to n d phi by d theta, so dt. So where it is formulated as induced EMF equal to minus n d phi by dt. So where E is the induced EMF, N is the number of turns in coil, B is changing of magnetic flux. Sorry, phi is the changing of magnetic flux, d phi is the changing of magnetic flux, dt is change in time. The negative sign in Lenz law indicates that the induced EMF in the coil is, why negative symbol? The coil is in the opposite direction of the magnetic flux, which is linked with the coil. The induced EMF in the coil is in the opposite direction of the magnetic flux, which is linked with the coil. Applications of Lenz law. Lenz law is used to determine the direction of induced current, and it is also used in eddy current balance, metal detectors, eddy current dynamiters, braking systems on train, AC generator, car radiators, microphones. What is Lenz and Faraday? Lenz law is conservation of energy applied to the electromagnetic induction. Conservation, see, Lenz law is a conservation of energy applied to electromagnetic induction. The conservation of energy applied to electromagnetic induction. What is Faraday law? Faraday law is electromagnetic force produced. It is produced, that is applied. See, Lenz law is a conservation of energy applied to electromagnetic induction. Faraday law is what? Faraday law is a electromagnetic force produced. This is force produced, that is applied. What is magnetic flux? Just we discuss in our concept what is magnetic flux changing, the rate change of the magnetic flux with time. Let's see what is exactly magnetic flux. A measure of strength of the magnetic field passing through a surface perpendicular to the field. A measure of strength of the magnetic field. What is that magnetic flux? Magnetic flux is nothing but a measure of the strength of the magnetic field. It is strength of the magnetic field measurement passing through a surface perpendicular to the field. Passing through a surface perpendicular to the field. For a bar magnet, the flux is maximum at the pole. For the bar magnet, what is the flux? The flux is maximum at the pole. The more magnetic field lines, the high in the flux. So if there are more magnetic lines, then the magnetic flux will be high. What is magnetic flux? The measure of the strength of the magnetic field. The measure of the strength of the magnetic field is called as magnetic flux. Magnetic flux is maximum at the poles for the bar magnet, and in the similar way, if your more magnetic fields considered in the if more magnetic field lines, then strength of the flux also high. So this is about the schematic diagram. So this is about the normal area of surface. Throughout this normal area of surface, the lines are passing. The lines which are passing through this magnetic field, magnetic surface, or this particular surface area, it will be considered as a magnetic flux, and it is simply represented as mathematically phi equal to BA cos phi, where phi is the flux, B is the field, A is the area. When a conductor moves through a magnetic field, a force is exerted. What is happening? A force is exerted on these charges, causing them to separate, induced EMF. So here, what is happening? When a conductor moves through a magnetic field, a force is exerted on the charges, causing them to separate. So what is separate? A force is exerted on the charges. So positive charge and negative charges both will be separated. And what is happening? A EMF produced. That EMF is called as the induced electromotive force. You can see the figure here. So positive charge and negative charge. The EMF. So the EMF result when the conductor has velocity component perpendicular to the magnetic field. So here the EMF results when the conductor has a as a velocity component perpendicular to the magnetic field. So F stands for the force, V stands for the velocity. We know that from the work energy concept. So here the work is nothing but it is a force and distance or displacement. You can consider W equal to F and D, and V equal is what? V is the velocity. Sorry, here V stands for the velocity. Sorry, V stands for the velocity concept here. Then here we can consider here V equal to W by Q. Therefore, V equal is what? V equal to FD by Q. But from the Lagrange force, F equal is what? QVB. Then from the substitution of F value in V value, so we get F equal to FD by Q. So what is F value? F value is BBQ. Simplify. Therefore, V is small v is the voltage and capital V is the velocity, and D is considered as L, which is nothing but length. Sorry, here I can consider as this is about the voltage. So here the work is considered as the force and displacement, and voltage is considered as the work done by with respect to charge. There is a small mistake, not small, it is a mistake. So V is your voltage equal is what? Work done by the charge. Therefore voltage V equal from this concept W equal to FD. So V equal to is what? W by Q. Then replace the V value here. V equal to FD by Q. From the Lagrange concept, F equal to QEB. Then substitute the value of F and V related. Then V equal to FD by Q, where F is BVQ, D Q, and simplification V equal to BVD, where small v is the induced EMF or voltage, V is the velocity, D is the distance or displacement, which can be considered as L, which is length. Therefore, voltage or electromotive force is equal to BVL. What is that? V equal to BVL. Then this is what? The voltage in a circuit is equal to magnetic field, velocity and current. Now what is the relation between electromotive force and magnetic flux? We know that electromotive force or V equal to BVL, where V is the velocity, Therefore v is what? Distance by displacement. So velocity is equal to displacement by time. Then I am taking two point of position, that is x minus x naught, time also t minus t naught. So therefore the induced EMF del x by del t, what is EMF? V equal to BVQ. In the place of V, what I am taking? In the place of V, I am taking that one, delta x by delta t. So delta x by delta t into BL. What is delta x by delta t? X minus x naught by t minus t naught. So simplify here, xl minus x naught L into, so here multiply with the L, xl minus x naught L into B t minus t naught. Then you take something here. What is that something here? X L is nothing but A. So you can simply take that one, BA minus BA naught by T minus T naught. But phi equal is what? But phi equal to BA cos phi, that means BA. Therefore, the relation between EMF and flux is considered as what? EMF and flux is considered minus d phi by dt or minus del phi by del t. That is only now. So here EMF equal to delta x by delta t into BL, where delta x by delta t equal to xl minus x naught L into B t minus t naught. Xl is nothing but A. So BA minus BA naught. So where BA is the BA cos phi is the phi. So here simply I am taking that one, phi equal to BA. So leave it the cos phi. So cos theta, leave it. Then phi equal to BA. Then replace here. You will get that one. Here that is the thing is that you need to understand. Phi minus phi naught. So but what is simple one? Phi equal is what? Phi equal to BA cos phi. This leave it. So phi equal to BA. Therefore induced EMF V equal to, or voltage induced EMF R V equal to, what is that one? BA minus BA naught by T minus T naught. So here this is phi naught. So minus of phi naught minus phi. So sorry, minus of, here you will get the formula, phi minus phi naught by t minus t naught. So here this will be delta t, that's no difference, so it simply remain. But here you need to consider this phi minus phi naught, that means we need to take phi naught minus phi naught. So that is the reason it will be taking as a minus symbol. So del phi by delta t. Understood this one? So here what is t? Delta t is nothing but t minus t naught. That's simple. But here what is phi? Phi must be phi minus phi naught. But why we are taking formula? It is reverse form. That is phi naught minus phi. So here EMF equal to minus del phi by delta t. Induction is a process which is proportional to the rate change of the magnetic field. Induction is also known as inductance, where L is used to present the inductance and Henry is the unit of the inductance in SI method. Henry is defined as the amount of inductance required to produce EMF of 1 volt in a conductor. So we have no time, that's the reason I am moving quickly. Henry is defined as the amount of inductance required to produce an EMF of 1 volt in a conductor. When the current change in the conductor is at a rate change of 1 ampere per second. So what is the units of Henry? Unit and so what is Henry? Henry is the unit of this inductance, where L is represent inductance. So what is the unity definition of Henry? Henry is defined as the amount of inductance required to produce an EMF of 1 volt, one EMF of 1 volt in a conductor. So when the conductor changes, when current changes in the conductor, how changes current to 1 ampere per second? According to 1 ampere per second, there is a voltage changing According to voltage change, that is induced EMF produced. So this is nothing. If all are uniform, then it is equal to 1 Henry. So here inductions are how many types? The inductions are two types. One is self-induction, the another one is a mutual induction. Let's see what is a self-induction. Self-induction is a phenomena of inducing EMF in the self coil due to change in a current and hence the change in magnetic flux in the same coil. Self-induction is a phenomenon of induced EMF in the coil, which coil? Self-coil, due to change in current and hence the change in magnetic flux in the same. Because of the current, in the flux also there will be variation, but when you are changing the current in the same coil only the flux will be variation. So here if you are taking a coil, so in the same coil if you are changing the value of current, according to changing of current the flux value also will be changing. Sorry, the flux value also will be changing. So here in the same coil the current and flux both will be dependable. We are taking the coil, and to this coil if you are applying current, if you are variation of current, according to variation of current the flux also will be variation in the same coil. So this is called as self-induction. The induced EMF opposes the growth or decay of current in the coil and delays in the current acquire maximum value. So this is further on we can see in the coming session. So here just go here, you can see here the self-induction is the phenomenon of inducing EMF in the self coil due to change in current and hence the change in magnetic flux in the same coil. Because of changing current, magnetic field will be flux will be changing. Here flux and current both are in the same coil. So this is called as self-induction. The units of self-induction we already discussed, that is an Henry. In mathematically it is taking as phi is proportional to height. Where is phi? What is phi? Phi is nothing but flux. I is nothing but current. Then phi equal to, if you remove the proportionality, phi equal to Li, where L stands for inductance. If I equal to is 1, if the current unit is 1, if you are taking current is 1 unity form, then L equal is what? L equal to phi. So therefore, the self inductance is defined as magnetic flux linked with the coil when unit current flows through it. When unit current flows through it. If you are taking the current in a unit form, means one unit form, then the flux in self-inductance is what? In self-induction, the flux is considered as L equal to 5. Inductance is equal to, sorry, inductance is linked to the flux. Inductance is linked to the flux. That means L equal to 5, where phi is proportional to I. Therefore, in the place of proportionality, we are taking constant. That is phi equal to Li. If I is a 1, that means unit current flows. Then L equal to 5, where L is the constant proportionality and is known as self-inductance or coefficient of self-induction. Also, if you are taking induced EMF from the previous Lenz law, so induced EMF E equal to minus d phi by dt. So just see what is phi. Phi is nothing but L I. Is it right? Phi equal is what? Phi equal to the Li. Is it right? Phi equal to Li. Then simplify d by dt of phi. Phi equal is what? D by dt of Li. Then L is a common. Then di by L is a common. Then di by dt. If di by dt is 1, if di by dt is 1, then what is happening? L equal to E. E means what here? Induced EMF. Is it right? If di by d, the rate change of current is 1, then L equal is 1. L equal is E. That means the self-inductance is defined as the induced EMF set up in the coil through which rate change of current is unit. So here in the same coil, induced EMF also generated. Induced EMF also is introduced, is set up when the current rate change of current is unit. When d phi by dt is 1, according to d phi by dt, if it is 1, then inductance, the self-inductance L is equal to induced EMF. That means in a coil, when di by dt is 1, then induced EMF also is linkaged. When you see the solenoid, what is the self-inductance of solenoid? Magnetic field due to the solenoid is, so this already we discussed in the previous slide, the previous video. B in the solenoid, what is the magnetic field due to solenoid? That will be B equal to mu naught Li. Sorry, B equal to mu naught N. So here what is magnetic flux linked across one turn of the coil is what? That is BA. So what is B? Mu naught NIA. So here what is I? I is nothing but current. L is nothing but length. So magnetic flux linked across n terms of the coil is what? So that is phi equal to. So you take from this one. Phi equal is what? This is mistake here. Phi equal to BA. So here phi equal to mu naught n square Ia by L, where phi is what? Li. So what will be happening? So it will be considered I will be cancelled. So what is phi? Phi is nothing but L. So I will be cancelled. So phi equal is this. What you will get? L equal to mu naught n square A by L. So what is capital N by this L? It can be considered as n square. N, number of turns per length, can be considered as n. So this is about the self-induction, where is n is the number of turns in the coil, phi is the magnetic flux, I is the current in the coil. Next, coming to other one, that is about the mutual induction. Mutual induction is defined as the property of the coils that enables it to oppose the change in the current in another coil. So here we are taking two different coils. So here coil 1, coil 2. If you are taking the current in this coil, if you have variation in the current in this coil, according to this variation coil, there is a magnetic flux changing in this coil. There is a magnetic flux changing in another coil. This is about the mutual induction. Mutual induction is defined as the property of the coil that enables it to oppose the change in the current in the another coil. With the change in the current of one coil, the flow change to induced EMF in the other coil. The induced EMF or flux will be changing in another coil. This will be known as the mutual induction. Mutual inductance is a basic operating principle of transformers, motors, generators, other electrical components that interact with the magnetic field. Then it can be defined as the current flowing in one coil that induced a voltage in another adjacent coil. This is about the another definition. If you are passing the current in one coil, in another coil the induced EMF is generated. So what is the statement? So here phi 2. Phi 2 means what here? This is, I am taking two different coils. This is flux of the coil is phi 1 and this is phi 2. And if you are applying current to this one, and in this coil there is a change of EMF. So that is the reason phi 2 of I1, or if you remove the proportionality, then it will be considered as a, so phi is what? Phi is nothing but a flux, I is nothing but a current. Phi is proportional to I1 of us. So the second coil flux is proportional to first coil current 2. So that means phi 21 equal to M1, Mi1. Where if you are taking I1 is 1, current in first coil is 1, then what is M equal to 5? What is M equal to? M equal to 5. So here the mutual inductance is defined as the magnetic flux linked with the secondary coil when current flows through the primary coil. So that only magnetic flux linked in the secondary coil is equal to the current linked to the primary coil. When M is a constant proportionality and is known as the mutual inductance or coefficient of mutual induction. Also, if you are taking EMF, induced EMF in the second coil, that is E2 equal to d phi 2 by dt. Again, if you are taking what is phi, phi is nothing but phi 2 is nothing but what? That is M. Is it right? So you can take that one. Phi 2 is nothing but M is nothing but phi 2. If you are taking phi 2 here, what is phi 2? Mi, mutual inductance. So you take that one. I is what? I is nothing but again di1 by dt. If di1 by dt is what? The derivative will be goes to 1, then M equal to E. That means mutual inductance defined as the induced EMF set up in the secondary coil when the rate change of the current is in primary coil. So here, if you are setting the current in primary coil, the induced EMF set up in secondary coil. Mutual induction in the solenoid. So if you are taking the solenoid, that is, if you are taking the field coil 1, that is, a magnetic field with the primary solenoid is what? B1 equal to mu naught N1 I1. Magnetic flux linked with the across one turn of the secondary coil is what? That is phi 2 per turn is equal to B1A. Where is what is B1? B1 is the mu naught N1 I1A. So simplify here. Capital N by L is nothing but small l. Is it right? Capital N by, oh my god, N by small l. This is small l. So here, magnetic flux linked across the n terms of the second coil. Second solenoid is what? Phi 21 equal mu naught N1 N2 N1 A by I. But phi 21 is equal to M21 I1. Replace the values here. Then mu naught N1 N2 A by I1. Then it will be simplification. You can see that one. What is that one? It will be mu N1 N2 A I. So this is about this. So finally we can conclude that one. For two long coaxial solenoids of the same length of cross-sectional area, the mutual induction is same and leads to the principal reciprocity where M equal to M12 and M21.